Okay, so today I'm going to talk about JIT compilers for scientific computing in Python. And it's Numba versus JAX. So, oops. Oh, it doesn't work. Okay. Context. So why do we use Python in HPC? So I'm going to tell you why I use it first. So I myself is a cosmologist. I did my PhD in CMB data analysis. And we basically process on the order of 10 terabyte up to a petabyte of data for cosmological inference. And we use scientific software in Python, and it's running on NERSC. So it's a top 10 HPC system. HPC stands for high performance computing, also known as like supercomputers, very, very fast. Yes, sorry, I haven't mentioned it. It's cosmic microwave background. It's everywhere, and every time you look at the sky, you will see that, but you don't know about it. You didn't know you see it. So, questions. So by the way, please help me. When I ask a question, please answer it. So which language can you use to write application for HPC? By that, I mean language that has demonstrated to scale to state-of-the-art, like full system supercomputer. It's not just use a language like Bash in a supercomputer. Options? Fortran, yes. And C and C++, and? Pardon? Why do you use Python? The next answer is actually Python. And you might call that cheating a little bit, because you know many codes that you actually like call in Python to run on HPC was written in Fortran or C or it's just exposed as a module. But it's still very useful as the glue to glue everything. And there's actually one more on this list, Julia. But not MATLAB, not Rust, they haven't like demonstrated you can scale the full computer yet. So another question, so why Python in HPC? What is its superpower in supercomputing? What would your answer be? Yes, embarrassing problem can be tackled in Python, but even like if it's not embarrassing parallel, you can also do it with Python. But why would you, even let's say your code is completely written in C++, why would you want to use Python?
It's faster to write. Yeah. Developer efficiency.
Yes, it's related. And I haven't put it here, but my answer is, because it's where the computer is, I'm not like trying to explain like how it got here or like would it still be the case in the future, but at least at the moment this is where the community is. And another reason, I don't know if it's a blasphemy, but we are the people who don't care what language our algorithm is implemented in. Right? C exposed as C module, even C Python is written in C. C++ using Python 11, which is demonstrated yesterday as Python module. And then Fortran, like SciPy, in SciPy many functions are actually written in Fortran. Even in Julia. If you write something in Julia, you can expose it with a Python interface. Rust, yeah. I almost forget, but not so much in HPC, but we do that. Some people do it in Python. So context, why JIT? So I'm trying to answer that, but I need to give you some short introduction first. So this short introduction of like compilers versus interpreter and AOT versus JIT. So first of all, we all know interpreters. C Python is an interpreter. Bash is another like commonly used interpret language. And I would say like on the HPC space, actually like Python kind of like replacing what Bash has been doing. Compilers, you traditionally have something called, I guess in the past you won't even call it AOT, it's just compilers. They compile things ahead of time. So there's something called GCC, CLang, something like that. And again, CPython is, I mean, it itself is an interpreter, but it is written in C, and is ahead of time compiled via one of, I mean, you can actually choose them, one of these compilers. And traditionally, they excel at XPC, etc. So how about JIT? We have actually, I mean, it didn't get taught a lot, but it got mentioned in this conference, PyPy. So it's actually just-in-time compiler of the Python language. So supposedly, any lightweight Python can be run by it. So Julia and JavaScript also have a JIT. And then I need one more short introduction, which is how you can accelerate a piece of Python code if you need to, right? So you could do ahead of time compilation. So you write something in C with CPython API, and then your code is fast. One of the very prominent example is NumPy itself. You can also have something like Cython, which is a superset of the Python language. Then you compile to C module, etc. And then we have Python 11 that got mentioned already. Or you can go to the JIT route. You have PyPy, which is, again, any program can be, any valid Python program can be run using PyPy. CPython itself, actually yesterday, just here, we have a talk on that. It also has an explanatory. Again, it's something like any valid Python program can be run, but actually like only a subset of your code will sometimes be just-in-time compiled. Or you could have something like Numba and JAX, which is the main topic today. That it can only just-in-time compile a subset of Python, and it mostly focus on like numerical evaluation. So my answer to why JIT is the most important answer. The most important point there is it solves the two-language problem. So you no longer need to use two different languages to implement like a very high-performance code. So for example, I'm showing one example on the left here. So let's say you start with a NumPy function, and then by adding that one single decorator there, you have accelerated that code by 3 times. And you could take this piece of code and we implement it in C++ and using Python 11 to expose it with a Python interface, which is what I actually have done in that commit. And the headline there is 14 files are touched, and there's 230 lines of code are added. So a lot of them are like boilerplate, glue code, but that's kind of the point. It takes a long time to do that. It can be done, and it's actually faster, 30% faster, but it's 30%. One single line there is 3 times. So there are other reasons, but I'm not going to mention it now. So in the next session, I'm going to give you one very concrete example and see how we can take it to run it with just-in-time compilers. With one example in Numba and then JAX. So let's take a look with this equation first. So this is the equation we need to implement. Just stay it and think about how you would do it. So as usual, if you want to implement in NumPy, we vectorize everything, right? So the function here is actually not very long. It's almost like a one-liner. I just break it into a lot of, I give you a lot of white space to make it clearer of what is happening. But it's one-liner. It's just implementing the math as we are written there. And it's quite fast. And how would you take this and just in time compile it in Numba? You just add a decorator. That's what I did. Is a little bit complicated. The one that really make a difference there is parallel equals true. It's a very simple decorator. You just add there, and you can immediately see that it's faster. And how will you do it in JAX? Can you guess? Just change the decorator. And one more thing, JAX.numpy. So it's not, in JAX, it won't, if you just use NumPy, it won't work immediately. But it has its own module, JAX.numpy. It's almost like a drop-in replacement. So whenever you have NumPy, you just replace it, usually called JMP, and then it will work. So in this case, it is. And you can see it's, again, much faster. So you can see this like general trend of progress that you start with something with NumPy, implement in Numba faster, we implement I mean, it's not even re-implementing, it's just changing how it's compiled, and it's yet even faster. It's general trend, but I'm not saying like this is always the case. So the question is it case closed? Can anyone spot any potential problems with this implementation? So basically all three implementations are the same, right? I'm going to give you a hint, it's here. This comment, what does it mean? It's the shape of the array that's being created at that region. And I need to have a digression in problem size. So I haven't told you how large the problem is, right? What's M over there? So Wij is an M by M matrix. M is the number of pixels. It can be as large as 70K. And the K there is the number of so-called visibilities. It can be as large as 10 to the power 7, right? So if you calculate the size of the array that is being created in that intermediate step is on the order of hundreds of petabytes, which is basically too much. You won't have a computer that will have it fit in the memory. And basically what you need to do, obviously, is to avoid the explosion of memory there with the K dimension, right? How will you do that in NumPy? For loop. Would that be efficient? No, probably not. I actually don't know how I can do it in NumPy efficiently. I think I can, but I can't prove I can. So let me know if you know a way. In Numba, however, you can write out that loop. So this function looks very similar to the version before, where this line is basically focusing on computing like that equation by fixing a particular K value, right? And then you loop over K, and then you do a in-place reduce sum of it, and that's all. And it's really, really fast. And one of the reasons is because I use something called p-range that parallelizes it. Okay, so far so good. How will you do that in JAX? It's very tempting to just replace the decorator, right? Because it's kind of like the promise of having that decorator. When you put it there, it will work, right? But it won't. In order to make it work, you need to write something like this. So the reason it would not work, like if you take this and changing it to a JAX decorator, it won't work because of this in-place manipulation. JAX dislike anything that is mutating your state. So because JAX is enforcing like a functional paradigm. It don't like things being mutated. And in order to represent exactly the same logic, you need to refactor it in this certain way that you have a certain like kernel function. Again, evaluating exactly the same equation by focusing on one particular K value. And then think about how you can tell the program to like go iterate over all K and then sum them up, right? So one of the idiomatic JAX way to do it is this interface, the scan interface, which is like a functional programming paradigm construct. And if you believe me, then basically this is how you do it. So this is represented almost exactly the same thing as this, but in a so-called JAX idiomatic way. So in the next session, it will be a bit more dense. I'm going to tell you a summary of like how Numba versus JAX on paper based on my experience. And I know that I'm short on time, so I will skip some of this. So what is Numba in JAX? So Numba, as a formal introduction here, is a JIT compiler powered by LLVM. It's carrying CPU only. It has a number.CUDA interface, but it's separate, and it only focuses on CUDA. JAX, on the other hand, is a tracing JIT compiler powered by XLA compiler. XLA is related to linear algebra, so you can see what their focus is. It's originally designed for machine learning workflow, but because machine learning and scientific computing has many similarities, it's also useful here. And the emphasis of having no sign effect. So it almost enforces functional paradigms there. It targets all the, basically, like all the different architectures there is, CPU, GPU, all different vendors, and even the TPU that Google has, because it's created by Google. And while I put the bullet there, both of this is trying to solve the two-language problem. So you can use one single language to implement like everything. But JAX is good also at solving, I call it like the three implementation problems, meaning that you don't need to re-implement it for different architecture and how you run it. Another tips I would give in thinking about them is you better think about it, this thing like Numba or just this entity to be both a language, a compiler, and a library. So it itself is a language, meaning that a domain-specific language, meaning that not everything can be just in one compile. Something is compiling it, and also it comes with a set of libraries. So in the following table, I'm going to summarize a little bit about that. So as a language, Numba is more like C-like mini language. Mostly anything you can express in C kind of can be expressed in Numba, while JAX itself is an even small language. What I mean is, there's more restriction on control flow, mutation, dynamic shapes. You basically can't do any of this. As a library, what Numba do is, I'm over here. So it implements a subset of Python and NumPy, and with a certain parallelization model. NumPy in Numba is a drop-in replacement, but only a subset of those operations are implemented. And whenever within the Numba just-in-time compile function, NumPy is called, they are actually being hijacked. So it's not really calling the NumPy library. Numba is taking over it and do its own thing there. But on the other hand, in JAX, it implements a subset of Python, NumPy, and also SciPy. So it's more library, a larger library. And they have their own namespace, JAX.NumPy, JAX.SciPy. They have similar API compared to NumPy and SciPy, most of the time the same. It has their own documentation. But because of that, it facilitates some deviations in behavior. Because JAX has some restriction, for example, in the functional paradigm we mentioned, and I'm going to skip the other stuff. So let's take a look at the table. Sorry. Okay, one thing I want to show you is if you have to pick between the two of them, Numba and JAX, like based on my experience, this is a flow chart. So this is like not how do you say? This is not the only thing you can do, but based on my experience, for example, there's one situation, Numba is actually better than JAX. So you only target a CPU if you know you have a lot of CPU cores and it's not linear algebra heavy, then Numba is actually better in that aspect. But most of the time, JAX is actually quite good. So the next thing I want to talk about is why I actually have done this. So what JIT has enabled in our scientific computing, and in particular, in one example called PyAutoLens. So that is a project basically with a very complicated science code base that's originally implemented in Numba, and I am part of the effort that port the whole thing to JAX, basically. And there are some advantages. I wanted to mention what you see in our previous example, the W2 there, is part of a bigger calculation that is called a likelihood function. And the crash course on that is basically you want to find the peak of that function. So there's many, many input parameters, and you want to find the peak. And there's one thing I haven't told you about just yet is, so if you want to have a peak finding, of course you know that the gradient information can be very useful, right? Gradient kind of tells you like where the peak is already, so it's pointing you in the right direction. And JAX has another advantage there, which is something called auto-diff or auto-grad. So because things are now just enough compiled, right? Compiler, what they do, they transform code. You have some code written in some way and transform it into another way. So why not you use that, you leverage that to transform your function to its gradient as well. It can do that. And this is one advantage in assignment projects like this. So in the following, what I'm going to show you is a very short illustration of what it really looks like in action, right? So this is a bit dense, but on the right-hand side is actually a strong gravitational lensing pattern. And the question to ask is, out of all these very complicated parameters, how you would come up with a model that can predict exactly the thing on the right-hand side. And with the power of the likelihood function, and then all these Python libraries, which is what I mean by the community here, right? You need your function in Python in order to use all the facility that has been built in the community. And here is it. So on the top right-hand corner, you can see that the parameters are being iterated, and the image you see does not really resemble what you see in the previous slide. But now, as you iterate more and more and more, you see that it gradually becomes what it looks like in the previous slide. Okay, it's still iterating, but yeah, you get the message. Okay, so that all sounds good, but who won, right? In this particular case, like PyAutoLens, who won the battle of JIT? Can you guess? Of course, JAX, because our project is funded to put things in Numba to JAX. If JAX doesn't win, then we are basically a complete failure, right? But how much?
5 times.
5 times. Any other guess? 50 times. I'm so sorry about, I don't feel good about the typography, but the font is actually 50 times larger than the other text over here. It's that much. Okay, that's all of my talk. I'm just going to show you, these are all the people on the team, and then the links here, the QR code, and you can enjoy the rest. Thank you.
Thanks all, and now we break for lunch. Okay. Great job, Kolen.